In this example, you're being asked to write a complete arrow pushing mechanism leading to the expected major product. So these are all the same reagents that were in question number 2. So we already identified the substrate and the nucleophile. That's something we'd want to do here since we're trying to predict the product. So this thing right here, this species, this is the substrate, and here is the leaving group, the iodine, on that substrate. This species here is the nucleophile, specifically nucleophilic at this nitrogen because of that lone pair. The nitrogen in this case does not have a full negative charge. So we've already identified the substrate and the nucleophile, and we want to provide what the major product is going to be, and we want to give an arrow pushing mechanism leading to that expected major product. And what a mechanism is that's when you're going to use arrows to show how electrons moved, and that's how you're going to show which bonds formed and which bonds broke. It's a logical progression on how these reagents turn into the product. That's what your goal here is. So let me redraw this starting material, this substrate, and I'm going to show the bond between the carbon and the iodine here. And I'm actually going to put the electrons in on the iodine as well. Reason being is because when you're doing a mechanism, you're showing the movement of electrons. So you probably just want to show the electrons anyways. You don't have to. Most people don't, but I'm going to do it here. All right. Now, on this, let me put this carbon in red. All right, so remember that iodine is more electronegative than that carbon. It's pulling electron density towards the iodine, which means that carbon is ending up with a partial positive charge. And since that carbon is ending up with a partial positive charge, that means that it is susceptible to attack by things with electrons, like nucleophiles. So let me redraw this nucleophile here. And I'm actually going to switch up this substrate. I'm actually going to show the bond between the carbons and the hydrogens as well. All right, so we already know that the red carbon has a buildup of positive charge, so it's susceptible to a nucleophilic attack by nucleophiles. Well, the nitrogen in this case, on the species on the right, is the nitrogen is the nucleophilic atom. Those electrons are going to attack that red carbon. Now, that red carbon has 4 things bonded to it already. It has another carbon from the methyl group. It has 2 hydrogens, and has the iodine. In order for that bond between carbon and nitrogen to form, something has to leave that carbon. And the best thing to leave is going to be that iodine. And it's going to leave with an extra electron. Okay. Now, the reason that's the best thing to leave is because it's going to handle that negative charge the best, because it's polarizable. It has a lot more room for that negative charge, which means less electron repulsion. The other possibilities would have been the hydrogens. Can those leave with the negative charge? Well, H- is a really strong base. It's a really strong nucleophile. It's going to be very unstable compared to I-. So hydrogen's not going to leave. That's not going to be the first thing to leave. Carbon leaving with negative charge, that's also very unstable unless something is stabilizing it like resonance, which would not be in this case. So the best leaving group here is the iodine. That is the species that will leave. So what we want to show is we want to show those electrons between the carbon and iodine. They're going to stay on the iodine. And now we have a new bond between the carbon and that nitrogen. So we're not really interested in this species here. That's just the leaving group. We want to draw the major product. So we want to draw this species here. And now there's a bond between that nitrogen and that carbon. There's also still an ethyl group here and an ethyl group there, and that nitrogen had a hydrogen on it. So now that nitrogen actually has a positive charge because it doesn't have that electron anymore. It's being used in the bond. So we could say that this is the major product. We could also, I'll draw this in just to kind of show you what could be happening, but is very unlikely. The iodine could take that hydrogen and leave these electrons on the nitrogen, which means we would end up with this as the major product. And there's the 2 ethyl groups still bonded to that. But it's more likely that that nitrogen is going to hold on to that proton anyways, since the result of that would have been HI, which is a really strong acid. So I would say that the best major product to put here would be this species here. But it was still just an SN2 reaction, and that would be the major product.